We're wrapping up Unit 3 today. Means, of course, tomorrow is Unit 3 test. It should be posted out there in Blackboard for whenever you want to take it. Let me double check just to make sure I got it out there. It's been a long week, so I want to make sure I got that done. And it is out there for you, along with an extra credit assignment again for you to do with the test if you want extra credit. Tomorrow's class, like our other test days, I will be online, but I will be out here simply to answer questions. There will be no lecture or assignment tomorrow. I'll just be out there in case you have any questions off the test. So I will log in. I'll be on for the first 10 or 15 minutes or so. If nobody logs in that time, I will log out. As long as you have the test done by the end of the day tomorrow, you've satisfied any requirements for tomorrow. So it's out there. If you want to do it tonight and get it over with, you're welcome. That would end Unit 3. Now, tomorrow ends for us the end of week 7 for this semester. Being a 12-week class, that means we are over halfway there. We only have 5 weeks left. Our next unit, Unit 4, will take approximately 3.5 of those 5 weeks. Unit 5, we almost never get all the way through. We'll just have kind of a little abbreviated Unit 5 at the end. But we're getting close in a hurry, so make sure you're looking at your grade. If you're missing any assignments in Blackboard, let me know. If you look at the grade book outside of the test for tomorrow and the extra credit, everything else should be filled in. I don't have anything else in the grade book that isn't graded. Make sure you've got that grade book has scores for everything. If it doesn't, assignments themselves have the date of that assignment, so you can go back and find that assignment by date in our course information. Otherwise, let me know and I will help you find that assignment and get a copy to you. So today, the few things that we have to wrap up are kind of the odd pieces of units and conversion. We've talked a little bit about time and the standard time things, of course, 1 minute being 60 seconds and 1 hour being 60 minutes. We haven't got so much into the days of 1 day being 24 hours. All of those different equivalencies that I'm sure you guys are familiar with. But there are some units dealing with our metric prefixes that I want to talk about. In electronics, we've already talked about the metric prefixes and how they apply to volts and watts and ohms and amps and some of those electronics units. And the fact that they only use the major ones. They have the main unit. They use milli. And moving down. And then they use kilo, mega, giga, and tera going up. They skip those intermediate units like deci and centi and hecto.
I'll be back in a moment.
Yep. So this use the every 1,000 multiplying or dividing. Well, in electronics, electricity moves very fast. Not quite at the speed of light, but awfully close to it. Because electricity moves so fast, often our standard time frames are not adequate. They're too large. So we take our second and we divide it up into smaller pieces. 1 second, 1,000 milliseconds. Of course, the abbreviation there would just be ms. They usually shorten it to s for seconds. So 1 ms is 1,000th second. sometimes we need to get down even smaller than a millisecond. 1 millisecond contains 1,000 microseconds. That funny looking U is actually the Greek letter mu, which means micro, or 1 millionth of a second, or 1,000th of a microsecond. Now, how these typically come up when we're doing calculations is we might have a calculation of time comes out to be something like this, 0.0073 seconds. Obviously, it's an S, not a 5. You have to think in terms of that engineering notation. This is why we did the engineering note, or one of the reasons why we did the engineering notation back in Unit 2. We have to move the decimal point 3 spaces at a time. If I go 1, 2, 3 spots, that takes me from seconds to milliseconds. That would be 0.73 milliseconds. But we don't like, I mean, that's not bad, but we don't like having numbers that are smaller than 1. We would prefer to take that 3 more spots. First, we'd have to add a 0 there. Make that 730 microseconds. If we had 0.000028, and we move the decimal point 3 spots, that'd still be 0.0028. Takes it seconds. That takes it from seconds to milliseconds. That's still really small. We definitely don't want it that small. But 0.73 milliseconds probably could have lived with that, but 0.0028 milliseconds, too small of a number. So we move the decimal point 3 more spots, take that 2.8, and that takes it from milliseconds to microseconds. And going the other way is similar. If we have something that is 24 milliseconds, turn that into regular seconds. I take my decimal point. Now, since there's no decimal point here, it's at the end of the number. And we're going to move it the other direction to get to the larger units. We're going to make if the unit's going to get bigger from milliseconds to a full second, the number has to get smaller by 3 decimal places. So 1, 2, 3, we got a decimal point. That is 0.024 regular seconds. Or if we have 40 microseconds, and we want to convert that back into regular seconds. Well, first we would go to milliseconds. So again, there's no decimal point there, so it's at the end of the number. We go 1, 2, 3, adding a 0 makes that 0.04 milliseconds. Then convert to just regular seconds, we got to have to go 3 more spots. 1, 2, 3, filling in those zeros. That is 0.00004. Just regular seconds. So in electronics, those time frames become very important. Because things happen so fast, it's very important to have those smaller units of time, smaller than a second, in order to be able to time. Our last topic for the course is temperature. The standard system, temperature is measured in degrees Fahrenheit. I am going to look that up here on the other screen because I just totally blanked out on how to spell that. I did forget an H in there, that's why. F-A-H-R-E-N. I was close. So, standard system is measured in degrees Fahrenheit. In degrees Fahrenheit, we have 2 benchmarks that are used.
I think that we should do the metric system in Celsius. Not the metric system, but for
water boils.
degrees.
We are slowly making that switch. So in degrees Fahrenheit, let me change the color here. What temperature does water freeze at?
32,
32 degrees. What temperature does it boil?
212,
Well, good.
or
Well,
0 and
Metric equivalent is degrees Celsius. So in degrees Celsius, water freezes at what?
0,
0 and boils at
100.
100. So because
Be a
of that
lot easier.
difference, it's actually 100 degrees from water freezing to water boiling. The Celsius scale is actually sometimes called the centigrade scale. Centi meaning 100, grade meaning gradient or divisions. So you might hear someone say it's 20 degrees centigrade. They're really saying Celsius. Centigrade is kind of like a nickname for the Celsius scale. Celsius was actually the scientist that developed this temperature scale. Believe it or not, it was developed totally separate from the metric system, but was adapted as the metric temperature, so they didn't have to create their own temperature system. So 2 things to point out here. Number 1, we just said, in degrees Celsius, it is 100 degrees from water freezing to water boiling. But in degrees Fahrenheit, if I subtract 212 minus 32, that's 180 degrees from water freezing to water boiling, which gives us a ratio here of 180 degrees over 100 degrees. If I reduce that ratio, both of those can be divided by 20, gives me a ratio of 9 to 5. So an increase of 9 degrees in the Fahrenheit scale would be only an increase of 5 degrees on the Celsius scale. So 1 degree Celsius is a larger change in temperature than 1 degree Fahrenheit. Other thing we notice here that's actually the big issue in our temperature conversions is there isn't a common 0 point. That is a huge issue. What do I mean by no common 0 point? Well, in length, 0 inches equals 0 centimeters, or 0 feet equals 0 meters. In weight or mass, 0 pounds equals 0 kilograms. 0 ounces equals 0 grams. Capacity, 0 liters equals 0 gallons, no matter what you wanted to use to measure it. 0 was 0. There was nothing. Well, in our temperature system, 0 degrees Celsius does not equal 0 degrees Fahrenheit. There is not a common 0 point, which means we can't just use that simple dimensional analysis to convert the temperature. We have to use formulas. Because we're not just converting the size of the unit, we're converting where the 0 point is. So we have to do both things. We have to both convert the size of the unit size, and the 0 point. Well, there's 2 formulas we need to use. The first one is if I'm going from degrees Fahrenheit and converting degrees Celsius. This formula is Celsius temperature equals. So we start with our degrees Fahrenheit. The first thing we have to do is adapt that to convert the 0 point. Well, it's 32 degrees difference, so we subtract 32 degrees from the Fahrenheit temperature. Next thing we have to do is look at the size of the degree. Fahrenheit degrees are much smaller than the Celsius. So it's times the 5/9. that ratio of the size of degrees. If I want to go the other way, if I want to go from degrees Celsius into degrees Fahrenheit, Fahrenheit temperature does the opposite thing. Over here, we subtracted the 32 and then multiplied by 5/9. Over here, we're going to do exactly the opposite. We're going to divide by 5/9, or dividing by 5/9 is the same as multiplying by 9/5, and then we're going to add the 32. The opposite steps and in the opposite order. Let's look at an example. Let's take human body temperature. Let's convert 98.6 degrees Fahrenheit First, we have to figure out which formula we need. That'd be this one here, going from Fahrenheit to Celsius. We're going to plug the 98.6 for F. And now it's a matter of order of operations to solve that, find that solution. So we got to do the parentheses first. 98.6 minus 32 is 66.6. Then we'll multiply by the 5/9. 5/9 times 66.6. Now we don't need to put in fractions. We could just do 5 divided by 9 times 66.6. Gives us 37. So that is 37 degrees Celsius. Equivalent to 98.6 degrees Fahrenheit. So we've converted human body temperature from Fahrenheit to Celsius. Well, we might also look at, let's say you're driving in to school one day, and the weatherman says, or weather person I should say, says that it is going to be 20 degrees Celsius out there. You know, in 20 degrees, that sounds pretty cold. Well, is that really cold or not? So to do that conversion, of course, we're going to go over here from Celsius to Fahrenheit. We're going to plug the 20 degrees in for C, the Celsius temperature. So we have 9, again, it's order of operations. So we have 9/5 times 20. 9 divided by 5 times 20 is just going to be 36. And 36 plus 32 degrees. 20 degrees Celsius is 68 degrees Fahrenheit. I would take a 68-degree day pretty much any time of the year, but especially right now. I want you guys to try one in your notes. I want you to convert negative 40 degrees Fahrenheit Give you a minute and then we'll go over it. So let's take a peek. So we are going from degrees Fahrenheit to degrees Celsius. We are using this formula over here. We're going to start out, C equals 5/9, negative 40 in there for F, minus 32. We're going to do the parentheses first. Negative 40 minus 32 is negative 72. And we multiply. 5/9 times negative 72 is negative 40. Negative 40 degrees Fahrenheit is actually also negative 40 degrees Celsius. the one temperature that's the same on both scales. We can double check it, try to go back the other way. Negative 40 degrees Celsius. What does that convert into in degrees Fahrenheit? Oh, this formula to go the other direction. F equals 9/5 times negative 40 plus 32. 9/5 times negative 40 is a negative 72. And negative 72 plus 32 is negative 40. So it comes back to negative 40 again. I really wish that both scales had just somehow figured out a ways to make a common 0 point. Negative 40 just happens to be the common 0 point, but it really was not planned. It just worked out to be that way. There is another temperature scale out there called the Kelvin scale. Now, it's not degrees Kelvin, it's just a Kelvin. 0 Kelvin, 0 K, is equal to negative 273.4 Celsius. Now, I'm going to put a flash to that 0 so you know it's a 0 and I'm not saying OK there. 0 Kelvin is defined to be called absolute 0. It is the temperature at which there is no heat present. In other words, the atoms in a material stop vibrating. Even though this tabletop here, it looks like it's sitting perfectly still, the atoms inside that are vibrating back and forth. The colder it gets, the slower they vibrate. Until they hit absolute 0, they stop vibrating completely. There is no thermal energy available at all. Extremely cold. Nice thing is 1 Kelvin is equivalent to 1 degree Celsius. So 1 Kelvin would raise this, so I went from 0 Kelvin to 1 Kelvin. I went up by 1 degree. It would raise my Celsius temperature by 1 degree. Negative 273.4 to a negative 272.4 degrees Celsius. They at least did plan that out. Where we would use dimensional analysis with temperature. And that is if we have a temperature change. I have a heater that is capable of increasing temperature in a room. By 4 degrees Celsius per minute. I want to know what would that be in degrees Fahrenheit per. So I would still set this up, 4 degrees Celsius per over 1 minute. Just like we did our rates on Monday and then Thursday of last week as well. You have to get rid of the degrees Celsius and change them to degrees Fahrenheit. Now the 4 degrees here is not a temperature. It is a change in temperature. It's a plus 4 degrees Celsius. It's an increase of 4 degrees Celsius. So because it's a change in temperature, not an absolute temperature measurement on our thermometer scale, we can do our dimensional analysis to change it. We know that 9 degrees Fahrenheit, change of 9 degrees Fahrenheit is equivalent to a change of 5 degrees Celsius. I got those numbers backwards. Celsius is on bottom, so they will cancel out. 5 degrees Celsius is 9 degrees Fahrenheit. So the degrees Celsius cancels out. And of course here I still would have to change my minutes into hours. So I want to go from minutes to hours there. Minutes and hours, 1 hour is 60 minutes. The minutes cancel out. So on top I have 4 times 9 times 60. It'll be 2,160. That is degrees Fahrenheit. on bottom, I have 1 times 5 times 1 hour. That is 5 hours. I divide that by 5, I'm going to get 432 Fahrenheit per hour. Now that's obviously a high temperature. Chances are it probably can't really continue at that rate for a full hour. But it is the equivalent rate. A change in temperature of 4 degrees Celsius per minute is equivalent to 430 degrees Fahrenheit per hour. So that is all we have for Unit 3. We are back in the textbook for today's homework. Finished up the packet yesterday. In the textbook, there's 2 pages. There's page 154, looking at the metric prefixes used in our time conversion. 1 through 31, the odd. And also, page 156, in our Celsius to Fahrenheit conversions, 1 through 19, the odd. So remember, tomorrow, Thursday, March 4th, is Unit 3 test. We need to make sure you have that done anytime by the end of the day tomorrow. So with that, that is all of our new material for today, everything new for Unit 3 here. So we'll shut down the